Morning, everyone. How are we doing? Questions while we wait a few moments for everybody else to come in? Questions about yesterday's material? Anything? No? We're good? I'll open the first web work probably tomorrow. I'm just waiting until we do enough material. Otherwise, people can't do it thinking that there's something that they're not understanding, when in fact it's because we haven't covered the material yet. So I don't want to open it up too early. Probably tomorrow after class, I'll open it up. Questions? Anybody? No? We're good to go? We were looking at sequences and series yesterday. And we looked at important series. Series that not only do we know the convergence, but we know what they actually converge to. We'll see that this is quite rare. And in most cases, we're only able to determine whether a series converges or not what it converges to. We'll be looking at different tests today that give us exactly that. They give us convergence or divergence of a series, but they don't tell, I mean, in the case a series converges, it doesn't tell us what the series converges to. But before we get to that, Rebecca wanted us to consider number 37 of section 11.1. Which is the sequence 2n minus 1 factorial over 2n plus 1 factorial. Apparently I've typed 263 instead of 262. Of course it's 262. Thank you. I'll make the change after class. So let's consider this sequence here. And I mean, of course, you know that with a sequence, all you want to do is find the limit as n goes to infinity. So well, exactly that, right? I mean, we can simplify this expression. Let's look at that again. So what is 2n minus 1 factorial? 2n minus 1 factorial is the product of numbers 1, 2, 3, all the way to 2n minus 1. 2n plus 1 factorial is the product of numbers 1 times 2 times 3, all the way to 2n plus 1. Now my question to you is, what is the number that comes before 2n plus 1? Of course, it's 2n. And what is the number that comes before 2n? Well, that number is 2n minus 1. So now, if you are dividing these two, you see that a lot of stuff cancels. Everything cancels except the 2n and 2n plus 1 in the denominator. So this expression, this sequence, is really the same as the sequence 1 over 2n times 2n plus 1. And now it's very easy to determine what this limit is. This limit, as n goes to infinity, is easily seen to be 0. And there it is. All right, so the first test we're going to see today is a test which gives us a relationship between the integral and series. So it relates series and integrals via a test known as the integral test. Let f of x be a continuous, positive, and decreasing function. Where f of, let's start that again. And decreasing function on the interval 1 to infinity. Let f of n be an, then the series convergent if and only if the integral converges. We'll prove this for two reasons. The proof is nice and simple. And in the proof, there's actually more information than is written in the statement of the theorem. Let's draw a picture of what's happening, and the proof will come out naturally. We've got a function which is continuous, positive, and decreasing on the interval 1 to infinity. So, you start somewhere and you're decreasing. That's essentially what your function looks like. Let us calculate, well, first let's partition our interval 1 to infinity into subintervals of length 1. And now let's calculate the lower sum on this partition. So on the interval 1 to 2, where does the minimum occur? The minimum, your function is decreasing, so the minimum occurs at the right endpoint. Right? And what is the area of this rectangle? Well, it has height, f of 2, and it has width, 1. So that's the area of the first rectangle. On the next one, where does the minimum occur? Again, your function is decreasing. Minimum occurs always at the right endpoint. And the height is f of 3 times a width of 1. And so on for all the remaining subintervals. I do not recommend that you do 262 and 263 at the same time. This was a terrible mistake. I just my finger must have slipped. I meant to write 262 and it typed in 263. Please do not take 2 courses at the same time in the summer. Seems like a good idea. You're thinking to yourself, you'll get rid of 2 courses at once. It's a terrible idea. Terrible idea. You'll hate yourself once the midterm rolls around. And for the final, it's going to be hell. Do not take 2 courses at once. 262 and 263 are relatively straightforward courses where you should be getting an A in each of these courses. If you're doing both of them at the same time, it's going to be very difficult to get an A in both courses. In fact, it's going to be difficult to get an A in any course. Don't take 2 courses at once. So this is the lower sum. And of course, f of 2 is just A2. And f of 3 is just A3, and so on. So your lower sum is actually the sum from 2 to infinity of an. I'll give you a moment to calculate the upper sum. Repeat. What is the upper sum? On the interval, so upper sum. On the interval 1 to 2, the maximum, since your function is decreasing, the maximum occurs at 1. So this is f of 1 times the width, which is 1. On the next subinterval, maximum occurs at 2. So the area of that rectangle is the height times the width, and so on and so on. This is f of 1 times 1. So that's A1. This is A2. A3 would be the next one, and so on. In other words, the upper sum is your series from 1 to infinity. Now you know that the actual area under the graph is sandwiched between the upper and lower sums. So lower sum is less than or equal to the actual area under the graph, which is less than or equal to the upper sum. Lower sum is the series starting at 2. The area under the graph is the integral. And the upper sum, right here, is the series starting at 1. So you have this nice inequality, and if the series converges, meaning if this sum is less than infinity, then the integral is less than infinity. So if the series converges, the integral converges. Similarly, if the integral is less than infinity, then this series starting at 2 is going to be less than infinity. But you're just missing one term, the first term, namely a1. So if this is finite and you add a1, it's still going to be finite. It's not going to change the convergence. You're still going to have a convergent series. So there it is. The series converges if and only if the integral converges. But we can change this a bit. We can generalize this result. Right? I mean, notice what happens if we had started this at some value k. Right? So in particular, if your function had just been decreasing from k onwards. Yeah, the LF and UF are upper and lower sums respectively. If we have a function which is just decreasing from k onwards, we can generalize the result, right? And if you work out the lower sum from k onwards, the lower sum, right? The minimum is going to occur at k plus 1 on the first subinterval, and so on. So it's easy to see that this is going to be the sum from k plus 1 to infinity. Whereas the upper sum is going to be the sum from k to infinity. And the area is still, right? So I mean, this is going to be bigger than or equal to the area, which is the integral from k, which is less than or equal to the right? So, I mean, this is really just a generalization of this idea starting at k, and this is going to be k plus 1. Right? Just repeat the whole argument starting at k instead, and you get this. So, where am I going with that? Well, I mean, suppose you have a series which is convergent by the integral test. You can approximate what the series converges to by adding the first k terms, and then of course you're missing the terms from k plus 1 to infinity. So this can be thought of as the approximation, And if you bring this to the other side, right, you see that the difference between what the series converges to and your approximation, which is the sum of the first k terms, is just the rest. So if this is the approximation, then this is going to be the error. Right? This is what the series converges to, minus your approximation is how far you are from the actual thing. How far you are from the actual thing. So this gives us a way to not only approximate, but know how close or how far away you are. Right? Because this, the error, is less than the integral. We'll see an example of that shortly. But for now, let's just practice. Well, in fact, before we practice, let's take an important example, namely series of the form 1 over n to the p. These are known as p series. So let's take this example, and if p is bigger than 0, the function associated with this, 1 over x to the p, or x to the negative p, the derivative, well, so first of all, you know that this is continuous and positive. On the interval 1 to infinity. Let's take the derivative to see that it actually is decreasing as well, so that all the conditions of the integral test are met. The derivative is just this, or if you prefer, negative p over x to the p plus 1. And the numerator is negative, denominator is positive on the interval 1 to infinity. So this is negative on the interval 1 to infinity. So f is decreasing. So we are in a position to apply the integral test. So we can apply the integral test. Somebody's asking, shouldn't it be x to the p minus 1? Well, it's 1 over x to the p, which is really the same as x to the negative p. So you bring the negative p down and you subtract 1 from the, Let's apply the integral test. The integral test, the integral from 1 to infinity of 1 over x to the p, or x to the negative p. Well, you know it's an improper integral, so you know that this means the limit as n goes to infinity of the integral from 1 to n and what is that? This is limit of 1 over negative p plus 1, x to the negative p plus 1 from 1 to n. And this is as long as minus p plus 1 is not 0. So in other words, as long as p is not equal to 1. We will see an example of how to use the integral test to approximate what the series converges to momentarily. But first, let's do a few examples of just the integral test. So if p is not equal to 1, you get that. And this is one over minus p plus 1. N to the minus p plus 1 minus 1 over minus p plus 1. So the question becomes, what is this limit? Right, that's the only thing that depends on n here. So what is that limit? And that limit will depend on the actual exponent. Is the exponent positive or negative? If it's positive, the whole thing goes to infinity. If it's negative, you get a 1 over infinity, which is 0. So for convergence, what is that? This limit will be infinity if the exponent is positive. And if the exponent is negative, this is a 1 over infinity, so this part will be 0, and we will get minus 1 over minus p plus 1 if minus p plus 1 is negative. So this is what we want, right? So here, in other words, this is the same as what is this? This is p less than 1. And this here is p bigger than 1. So if p is bigger than 1, you get convergence. And if p is less than 1, you get divergence. What about if p is equal to 1? What happens then? Well, if p is equal to 1, let's look at the integral again. This is 1 over x to the p, or 1 over x, which is the limit as n goes to infinity of the integral 1 over x, which you know to be ln x from 1 to n, and that is just ln n, whose limit is infinity. So let's put all of this together into a nice result. What does the result say? Let's give it a name. The P series. It's called the P series test. Series of the form 1 over n to the P. This will converge. So this series converges if P is bigger than 1. And we showed divergence if P is between 0 and 1, including 1. And notice that if P is 0, this whole term is always 1, so you're adding 1 infinitely many times. And if P is negative, then it's really n to a positive power. So you're adding positive powers of n. This function is going off to infinity. So you're adding numbers that are just getting larger and larger. So this will converge if P is bigger than 1 and divergent otherwise. So there it is. That's what we just proved right now, the P-series test. Let's take a few examples from the book. Questions before we do so? Can we conclude divergent using the integral test? Absolutely. Absolutely, we can conclude divergence. It's an if and only if statement, right? So if the integral diverges, the series diverges. What happens if P is 0? If P is 0, this whole term is always 1. So you're adding 1 plus 1 plus 1 infinitely many times, and you get a divergent series. So 0 is included in values less than 1. There it is. Let's start off easy. I mean, if you have questions related to this, you can ask them immediately. Questions? I'll let you type it up while we do this one. An easy question here. Right? If you rewrite this as 1 over n to the 0.3, you recognize it easily as a P-series. This is a P-series where P is 0.3, 0.3, which is less than or equal to 1, so divergent. Everybody with us here? Consider this and convince yourselves now that this is not a p-series, right? You cannot rewrite this in that form. Whatever you do, never going to be able to do that. So this is not a p-series, but we can still certainly apply the integral test. Well, I mean, I'm jumping the gun here. We need to check certain things, right? The function associated to this is the function 1 over 3x minus 1, which you know to be positive, so continuous and positive on the interval 1 to infinity. We need to check for decreasing. Let's do that by taking the derivative. The derivative of this is negative 3 over 3x minus 1 squared. Numerator is negative, denominator is positive, so this is easily seen to be negative, thus decreasing. So all conditions of the integral test have been satisfied, and we can now apply the integral test. So let us apply the integral test. And we look at the integral from 1 to infinity of 1 over 3x minus 1. It's an improper integral, so this is the limit as it goes to infinity. Antiderivative, I'm sure you can do in your head. 1/3 ln of 3x minus 1. Is that right? And as n goes to infinity, ln of 3n minus 1 goes to? You know what it goes to. Exactly that. Infinity. The integral diverges, so the series diverges. How are we doing? We want to do a few more? Could we have used the comparison test with 1 over n? Absolutely. Absolutely. There are other things you could have done. We did not see the comparison test yet. We will see that momentarily. But absolutely. Shall we consider one more? Somebody's asking a question. We'll answer that question after class. Can we do it on -1 to infinity? If it diverges from 5 to infinity? Well, I mean, first of all, we usually don't want to start with negative numbers, right? And secondly, again, when you're dealing with a series, think about what's happening. You're adding infinitely many positive numbers together. The first finite few don't matter as far as convergence is concerned. If you're adding, even if it's 100 million numbers together, the answer will always be finite. It's from the 100 million first number onwards that is the issue. So that's why in the integral task, you could actually start at any value k that you want, as long as it is ultimately decreasing, continuous, and positive. That's really all that matters. If the series started at n equals 0, you could use the integral test. Again, that's the whole point, right? It really doesn't matter where you start. It's that it's eventually continuous, decreasing, and positive. That's important. The first finite few numbers don't matter, even if that few is 100 billion numbers. Well, we're not going into the Riemann zeta function for obvious reasons. So let's stay away from the Riemann zeta function. Consider this. Consider this. Your function is 0 at 1. So you see, first of all, that the starting point of 1 really doesn't matter here, right? I mean, you could start it at 2, and it would be the exact same series. The first term would have been 0 if you started it at 1. So now, this is positive, so it's easy to see that if you define your function f of x as ln x over x squared, this is continuous and positive on the interval 2 to infinity. The derivative, let's apply the quotient rule here, vu prime minus u v prime all over v squared. And if you factor out an x, this is 1 minus 2 ln x. So denominator is positive. This x is positive on this region. So as long as this is negative, we're good to go. And of course, for very large values of x, this gets as large as you want. And, you know, in fact, it's easy to see that if, when is this 1? This would be 1 when x is e to the 1/2. So for values bigger than e to the 1/2, the whole thing is negative. So it's eventually negative, and again, really that's all that matters. you can show that e to the 1/2 is less than 2, and consequently, your function would be decreasing on 2 to infinity. You could do a comparison test, but again, we have not seen comparison test yet in this course. So let's wait until we see it, and then we can redo this question using the comparison test, if you will. But for now, we are able to apply the integral test on the interval 2 to infinity. The only question that remains is, how do we integrate? That's right. It's the eventually decreasing that's important. Let's not take a limit necessarily. I mean, you could take a limit to convince yourself that for large values of x, this gets as large as you want. So you get 1 minus a large number, which has to be negative. Integration by parts is correct. U is ln x. dv is the rest. So du is 1 over x, and v is negative 1 over x. So this is negative ln x over x from 2 to n, minus gives us a plus 1 over x squared. So this is minus ln n over n plus ln 2 over 2 minus 1 over x between 2 and n, which is and as n goes to infinity, it's easy to see that this goes to 0. So the only thing we're really interested in is what is happening to that. So let's look at that separately. Ln n over n. This has the form infinity over infinity. You know what to do. Quick L'Hopital's rule. Derivative of ln is 1 over. Derivative of n is 1. Limit is easily seen to be 0. So this goes to 0 as well. And we're left with ln 2 plus 1 over 2. The integral converges, so the series converges. How are we doing here? How are we doing with the integral test? Questions? So let's do exactly that. Find the partial sum S10 of the series and estimate the error in using S10 as an approximation to the sum of the series. So you see, you understand what we're going to do, right? We're going to calculate the sequence of partial sums. We're going to work out what S10 actually is. First of all, let's say this. 1 over n to the 4 is a convergent P series where P is equal to 4 bigger than 1. Right, so we know that it converges We know that we can apply the integral test, right? Because, in fact, we proved it in general for P series. When P was bigger than 0, this was a continuous positive and decreasing function. It's a very nice observation from somebody on the chat that suggests that we actually know what this series converges to. Let's hold off on that. Let's approximate and see what happens, right? So what are we doing? We're going to use S10, the sequence of partial sums. S10 is the sum of the first 10 terms. So that's going to be 1 plus 1 over 2 to the 4 plus 1 over 3 to the 4 all the way to 1 over 10 to the 4. So, you can add those numbers using a calculator or computer, whatever you want to do. So, add those up, get a decimal value, right? I mean, it's going to be bigger than 1. I mean, do we want to, let's try to add that up. Maybe Wolfram Alpha can help us. Let me see. Here we go. Wolfram Alpha gives us a value of 1.08203,65849, and so on and so on. Let's stop it there, but there it is. As somebody points out, if you were not allowed, if this was a usual final, a sit-in final exam or midterm, you wouldn't have access to a calculator, so you could not calculate this actual number. But it doesn't matter. It does not affect the result. You would just say this is x10, whatever it is, and that's it. You move on. You can still calculate the error though. And that's what we're going to do. Right? So the only difference is you wouldn't have this actual number. So that's your S10. Now the question is, right, I mean, we know this series converges. This is your approximation. How good is it? Exactly that. The value doesn't affect the error precisely. So what are we doing, right? We're looking at this. This converges to some value. We don't know. We approximate by adding the first 10 terms. We are missing the terms from 11 onwards. Or if you bring this to the other side, you get this. And this is your S10, right? The sequence of partial sums, S10. So that is your 1.08, blah, blah, blah. And there is your error. The difference between what the series actually converges to and your approximation. But this is less than or equal to the integral from 10 to infinity. Right? From the proof of the integral test. So that will be an approximation to the error. The error is going to be less than this. So that tells you how bad you are or how close you actually are. Can we step the variable down by 1 for ease? I'm not sure what that means. But let's evaluate this integral, which is the limit as n goes to infinity of the integral from 10 to n, 1 over x to the 4. Isn't it 11 in the integral? It is not. It is not. It is 10 in the integral. If you look back at your proof of the integral test, you had the integral sandwiched between two series. The series on the left started one more than the integral. Question is, how do we choose k ourselves to approximate? We'll see an example of that in a moment. Well, I mean, the value of k does may come into play. Exactly, depending on how accurate we want the estimate. Let's finish that up. Let's evaluate this limit. Antiderivative from 10 to n, which is 1 over 3,000 minus 1 over 3n cubed. And as n goes to infinity, this goes to 0 So we're left with 1 over 3,000. And there you go. This number is within 1 over 3,000 of the actual sum. Can't we just subtract the approximation from the real value? Well, that's what I'm saying, right? This is your approximation, so this is the real value, whatever it is. Minus your approximation, 1.082, and that is less than 1 over 3,000. There it is. As somebody had pointed out originally, we actually know through other techniques, not seen in this class, but this actually converges. We know what it converges to. This thing actually converges to pi to the 4 over 90. So if you work that out and you subtract 1.082 blah, 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 you'll see that the difference is less than 1 over 3,000. How are we doing here? And as somebody else asked, suppose that an alternate question to this could have been, isn't the real value minus 4 plus 1? Yeah, so that's why I have the minus 1/3 here. Right? Well, what if the question had actually given you an error? Suppose they had said, how many terms must you add to get an error less than 1 over 3,000? So that's where a k would have come in here. And you would have made this less than 1 over 3,000. And then you would have solved for k, telling you the smallest number of terms you needed to add to get an approximation to within 1 over 3,000. Why can't we use the p-task convergence value? The integral test gives you convergence or divergence. It doesn't tell you what the series converges to. Some people are asking, how does this pi to the 4 over 90, where does that come from? Again, this is beyond us, but through other techniques, in fact, a technique that you would see in 263 when you do it perhaps next semester, not at the same time as this course. Mr. Patel, why are you still here? You were here yesterday. Do you have nothing else to do? All right, let's take another example. Questions here before I erase this? Let's do an example with some sort of given error. Well, I mean, let's do, all right. Let's do this. All right, here's the question. Right, first of all, we know that this series converges. It is a convergent p-series where p is equal to 2, bigger than 1. So we know it converges. We know that, right, I mean, we prove it converges using the integral test. So we know the associated function is positive, decreasing, and continuous. Everything is fine, blah, blah, blah. Question is, how many terms must we add in the following sense, right? You can add as many terms as you want, let's say k terms, but then you are missing the k plus 1 terms to infinity. So this is going to be our approximation. If you bring this over to the other side, you get this, and from the proof of the integral test, this is less than or equal to the integral from k to infinity. It has just occurred to me that Mr. Patel could actually be Carla. Is it Carla? I'm pretty sure it's Carla. All right. So here we go. Right, I mean, this error is less than the integral from k to infinity. So what do we want? We want the error to be within 1 over 50, right? So we want this to be less than or equal to 1 over 50. So this is what we're going to concentrate on. And the integral is the limit as n goes to infinity antiderivative negative 1 over x from k to n, which is 1 over k minus 1 over n. And as n goes to infinity, this goes to 0, so you just have 1 over k. So you see, you want the integral to be less than or equal to 1 over 50. Right, so the integral to be less than or equal to 1 over 50 translates into 1 over k being less than or equal to 1 over 50. So if you cross multiply, you see that k has to be bigger than or equal to 50. So if k is 50, right, I mean, you're going to choose the minimum, or if you wanted strict inequality, you know, depending on the question. If we allow for equal, you're going to take k to be 50. If we want strict inequality, you take k to be 51. It's all good. So in other words, i.e. the sum from 1 to 50 approximates the whole thing to within 1/50. Correct. You can choose any k as long as it's larger than 50. Of course, we're very lazy and we don't want to do too much work. With computers nowadays, it's no more work to choose k to be 500 than 50. But if you were adding these by hand 100 years ago, you want to do the minimum amount of work, so you'd only want to add all the way to 50. Let's do one more. Questions before we do so? Let's mix it up a bit. Find the sum It is coincidence. So the question was, is it coincidence that you have at least 50 terms for convergence to within 1/50? It is. It is in this case, right? Because the antiderivative of this is going to be 1/k. So it works out. If this had been k cubed, the antiderivative would have been 2k squared. And then k would have been very different. K would have been, in fact, 5 here. 5 would have worked. So it's very coincidental that it's the actual number. Consider this. We are looking for the sum, correct, to 4 decimal places, right? So, I mean, that's exactly what a calculator does. When you ask it to evaluate something on a small calculator, you only have 8 decimal places. So as long as those 8 decimal places are correct, you're good to go. So here, we're asking to approximate this so that the first 4 decimal places are correct. What are we going to do? We're going to, we need a starting place. So, I mean, what do the first 4 decimal places mean? 1, 2, 3, 4. So we're going to start. We're going to start with an error of 0.00005. This is only a starting point. Might not work. and somebody's asking, shouldn't the error be strictly smaller than 0.00001? Or perhaps there's only 3 zeros, whatever. Here's the issue. There's never a general answer to this. Let's take an example. Suppose that we had somehow calculated a number like we did before, right, with a 1.08, whatever, 0, 1, 2, 3, 4. So let's say that this was 1.08016. Suppose we had calculated a sum to be this, and if our error is to within that, if you add that to there, right, 0.00005, it could potentially change the 1. So that's no good. That might not be good, depending on what this number actually was. If somebody suggests maybe a 1 here, but you still have that issue if this turns out to be a 9. Well, now you're thinking to yourself, I'll be safe and say 0, 1, but 1, 2, 3, 4. If you have 5 zeros, 1, 2, 3, 4, 5 zeros and a 1, it changes that 9 to a 0, 1, and it's going to change that 1 to a 2. So you see the issue. No matter how close, how small of an error you start off with, there could always be issues. You never know. So we give ourselves a starting point of halfway to the next and see what happens. We'll have to possibly adjust along the way if there's an issue, but there's no way to tell in general. So we start with this. So start with this. First of all, consider the function x e to the minus 2x. We need to check that we can actually, so 5 here is random, yeah, it's halfway to the next, right? We wanted 4 decimal places, so 4 zeros and halfway to the next. Again, it's only a starting point. We may have to adjust along the way. So here, this function is certainly continuous and positive on the interval 1 to infinity. Well, I mean, again, you can start with whatever you want. The point is, we're going to have to, well, I mean, look, you see the problem is if you take 3 zeros and a 5, I think you're going to be in a lot of trouble. In a lot of trouble because you want the first 4 decimal places not to move. So if you have opportunity for movement here, it's probably not going to end well. And you're probably going to have to readjust. So continuous and positive is easy to see. Let's take the derivative. And the derivative is this. If you pull out an e to the minus 2x, you get that. And if x is bigger than 1/2, This whole thing is negative, so you're fine here as well. So this is there on 1 to infinity. Very nice. So we know that we can use the integral test. I mean, we're not even 100% convinced of the fact that this converges. I mean, it's kind of implied in the question, but we really should check. Does it converge? So let's do the integral. And how do we integrate? You know how to integrate. Integration by parts. So u is x, dv is e to the minus 2x dx, du is dx, and v is minus 1/2 e to the minus 2x. So this is minus x over 2 e to the minus 2x plus plus 1/2 e to the minus 2x dx. Sorry about that. A bit it's a bit crowded there. So an antiderivative of that is minus 1/4 e to the minus 2x so that is 1 over 2 e squared minus 1 over 4 e squared is actually a plus, and minus 1 over 4 e to the 2. As n goes to infinity, this goes to 0. As n goes to infinity, let's do this one separately. N over 2 e to the 2n. This has the form infinity over infinity. A simple L'Hopital's rule gives you 1 over 4 e to the 2n, which is easily seen to be 0. So this goes to 0, so you finally get 3 over 4 e squared. That's the answer. And there it is. The integral converges, so the series converges. Again, it was implied in the question, but we really should check. But now that we have, what do we want to do? We want to answer the question, how many terms must we add? So how many terms k must we add as an approximation to what the series converges to, right? So again, if you bring this over to the other side, and as a starting point, we suggested that we needed this to be less than or equal to 1 halfway to the next, right? So 4 zeros and a 5. All right, but this thing is itself less than or equal to the integral from k to infinity of n e to the minus 2n. So if this can be made less than 0.00005, then we're good to go. If this is less than that, then this will be less than that as well. And now, integrate. I mean, I've rubbed it off, but it's kind of still here. Right? It's integration by parts because it's the same function. I mean, what are these ends? This is x. So here, what did we have? This was minus x over 2 e to the 2x between k and n, minus 1 over 4 e to the 2x minus 2x from k to n. Right? If you just redo the integration by parts, this is what you get. Well, so somebody's asking, why did we have to prove convergence before? First of all, it's a nice exercise. Secondly, what if your series didn't even converge? What if the book or the person asking you had made a mistake? Would you waste all this time trying to approximate something that doesn't even converge? So I mean, like I said, the book probably doesn't make a mistake, but on an exam, my first question to you would be to prove that it converges. You start by proving it converges, and then we can ask the question, what does it converge to? And if we're not able to get the real answer, then at least we can perhaps approximate, and this is where this comes in. So integration by parts gives you that, I claim. Did anybody try it? Have I made a mistake? Is this correct? Right, so that's what that limit is. and this should be less than 0.00005. So now trial and error. What is the smallest value of k which makes this true? And again, that's where Wolfram alpha comes in. Let's work that out. Right, on a normal sit-in exam, this could not be answered. You absolutely would need a calculator for this. So these approximate so that the first 4 decimal places are correct, would not come up. But luckily for you, you're writing take-home exams. So you should expect this kind of question. So what do we do? If k is 3, this term has been calculated to be terrible, 0.0043 something, so that's no good. If k is 4, zero, zero, 3075. Still no good. Right, well, I mean, why? So the question comes up, what about this need to adjust business? Let's not worry about it. Let's not worry about it for now. Let's just start by figuring out. So if k is 5, we have 0.0001, 248. Still no good. Should have probably started with something 1, 2, 3. 1, 2, 3, 4 zeros and a 1. There you go. 4 zeros, 1, 9, 9, 6, 8, and so on. Right? So is everybody with us here? This is what we're looking at. And you see that for k equal to 5, you're in trouble. Because there's no way for you to guarantee that the 4th decimal won't change. So we need at least 6 terms. And now let's look at what the sum of those first 6 terms actually is. No Bernoulli stuff. Let's look at what this is. So again, let me go back to Wolfram alpha. And Wolfram alpha gives us this sum as 0.18, 10, 0.85, blah, blah, blah. Is everybody with us? So you see, by making the sum less than 0.00005, we actually made the sum quite less, 0.000019968. And if you add or subtract 0.000019968, well, I misspoke there. I said add or subtract. If we subtracted, we'd be in trouble. If we subtracted, we'd be in trouble because it would change this. But there's no need to subtract because you know that you're adding only positive numbers. So you cannot have overstepped the approximation. In other words, this is always strictly less than the approximation. You never have to subtract. So if you add this to that, you see that the first 4 decimal places are actually not affected. So k equals 6 is fine here. And this would be your approximation, which is correct to the first 4 decimal places. If it had turned out that this had been an 8, possible, right? If it had turned out to be an 8 here, then you would have been in trouble because adding this to that would change this 0 to 1. And there would be no way for you to know if it's actually 0 or 1. And then you would have had to go to a smaller error and make sure that the first 4 decimal places are what you want them to be. But we don't have that issue here. This is a 0, and we're good to go. How are we doing here? Questions? Anyone? No? We're good? Let's move on then, if there are no questions. Can we explain it again why we are adding them up? Well, what were we doing? We were looking at, we are approximating we said that this was the sum from 1 to 6 plus the sum from 6 to infinity. And we worked this out. This was that. And this was less than 1, 2, 3, 4, 1, 9, 9, and so on. So you see that if you add these two up, it does not change the first. Yeah. And let me point out that this is always positive. So this plus this is bigger than just this. And that is 0.18, 10, 0.85, and so on and so on. So this thing, this value is sandwiched between, let's write it down properly here, your series, what the series converges to by this observation is sandwiched between 0.18, 10, 0, 85 and the sum of the two, which is 0.18, 10, 4 zeros, 1, 2, 3, 4. And this is, so 2, 8, 4. So whatever it is, right, you see that the first 4 digits don't change. Can't we just have started with 0.00001 as an error? That's fine, but you still have to check because it might not be good enough. So you always need to check. You always need to check. Vivian is asking a question I'm not sure I understand here. If the second bit of the series starts at 6, shouldn't the first bit start at 5? Are you saying here from 6? Yeah, thank you. This should have been 7. Thank you. Thank you. Not 5, yeah. So 7. But this is what we had looked at anyways, right? Yeah. Thank you. What if we check the sum first? What does that mean? So here the point 0.000199 is the error calculated from the integration, precisely that. Again, I'm still not sure I'm understanding the question here. Do you mean that if we know what the series converges to begin with, but if you do that, if you know what the series converges to, there's really no point in approximating it. That's the thing. We're not going to waste time approximating series we know. I mean, here, I know what that series converges to. So I am wasting my time here approximating it. but you don't. You don't know what it converges to, and that's why it's important to approximate. But there are series which no one knows what they converge to. In particular, the series 1 over n cubed. Right? I mean, we approximated the series 1 over n squared, but we do know what this converges to. This converges to pi squared over 6. Again, it's a result that's a bit beyond us, but it is a known result. Somebody pointed out the series 1 over n to the 4 converges to pi to the 4 over 90. Again, this is a known result, a bit beyond us as well. It's interesting to know that the series 1 over n cubed, nobody knows what it converges to. We know it converges, it's a convergent p series, where p is 3 bigger than 1. We don't know what it converges to. It's still an open problem. Nobody knows what that converges to. But we can approximate. We can approximate it in this fashion as precise as you want. So does this mean we use error to find k and then use k to check the sum to see if it impacts the first 4 decimal places? That's exactly correct. All right, let's move on. You can practice this tonight. As I said, these make for nice midterm and final exam questions. So you should expect that. So, in this, via the integral test, we saw a nice relationship between integral and series. And when we were looking at integrals last semester, in particular improper integrals, we saw there was a nice test to determine if an integral was convergent or divergent, known as the comparison test. If you can compare the integrand to a function, to another function, perhaps a simpler one, and if you know information about this simpler one, this could give you information about the integral itself, the original improper integral. Right? I mean, this was known as the comparison test. We have that same comparison test for series. So comparison test for series, suppose you have terms related in this way. Positive terms, only positive, right? Because all these tests we've been doing are for series with positive tests, for positive terms only. So suppose we have this. If the series Bn converges, then the series An converges. If the series An diverges, then the series Bn diverges. Let's prove it. The proof is one line. Trivial. If you have this, then the sum follows the same inequality. Inequality is preserved when you're adding Somebody's asking, how do we know the difference of two divergent series is convergent? We don't. We don't. It could converge, it could diverge, you don't know. You have to test every single time. So there it is, right? If the terms are related by this inequality, so is their sum. And if the sum of the large one converges, in other words, if it's less than infinity, then the small one is less than infinity. So if the large one converges, the small one converges. Conversely, if the small one diverges, if this is equal to infinity, then the big one is bigger than or equal to infinity. So it has to be infinity. So if the small one diverges, the big one diverges. There it is. Let's take an example. Consider this. Convince yourselves that this is not a p-series. It's not a geometric series. It's not a telescoping sum. Maybe. Probably not. You could maybe do the integral test. I'll leave that as an exercise. You'd have to show that it's decreasing. And the integration is non-trivial, but it's a nice exercise. All right. So otherwise, we're going to compare. We're going to compare this to another series. First of all, observe that -1 is less than 0. So that n minus 1, if you add n to both sides, n minus 1 is less than n. Very nice. So this series is less than or equal to n over n cubed plus 1. And now, let's look at the n cubed plus 1 business. You also know that 0 is less than or equal to 1. So n cubed, if you add n cubed to both sides, you get this. And if you multiply the whole thing by 1 over n cubed times n cubed plus 1, which is positive, the inequality remains. So this implies that 1 over n cubed plus 1 is less than or equal to 1 over n cubed. Notice that this is equivalent to cross multiplying. That's why cross multiplication works, because you're really multiplying by this. And let's multiply both sides by n, which is positive. So inequality is maintained. So what are we saying? We're really saying the series you started out with, n minus 1 over n cubed plus 1, is less than or equal to 1 over n squared. And this is a convergent p-series, where p is equal to 2 bigger than 1. So there you go. The big one converges, so the small one converges by the comparison test. How are we doing? Questions? Consider this. We're going, again, right? First of all, convince yourself that this is not, I repeat, not a p-series. If this minus 1 wasn't there, then you'd be good to go. But it is there. And you cannot get rid of it. Not immediately. You kind of can get rid of it by comparing. Minus 1 is less than or equal to 0. So if we add a root n to both sides, you get that. And if you multiply by 1 over root n minus 1, right, which is equivalent to cross multiplying, you get 1 over root n is less than or equal to 1 over root n minus 1. And what do you know about the series 1 over root n? This is a p-series. Is it? One over root n is a divergent p-series where p is equal to 1/2 less than or equal to 1. Exactly that. So here, the smaller one diverges, so the bigger one diverges as well. Let's do one more. Right, again, very similar to what we had there. So you might expect, right, I mean, for large values of n, this -1 here, or this +1, is really insignificant. It does not play a role. And consequently, you might expect the two series to behave in the same way. This one diverges, so you might expect this one to diverge as well. Can you use a comparison test if they don't start from the same value? Well, I mean, you're going to make them start at the same value, whatever largest value it is, right? Because again, the first million terms don't matter. It's only from 1,000,001st onwards. Can you multiply and divide by square root of n minus 1? Maybe. But here's what I was going to suggest. If you start off with the inequality you had before and add root n to both sides and cross multiply, you get that. And you see the issue. Or do you see the issue? This is a divergent p-series. But it's bigger than the other one. So there's no conclusion to be drawn. In the previous two examples, the inequality worked out rather well. This was bigger than a divergent p-series. In the previous example, if you look at it closely, you had your series to be less than a convergent p-series. Everything worked out nicely. Here, not so nice. Not so nice. The usual approach doesn't give you the right inequality. It gives you a series, a larger series, which diverges, and that is of absolutely no use to you. The smaller one could converge or could diverge, right? The inequality will be the same for the sum, and we're saying that this is infinity, so this is less than or equal to infinity. It could be less. It could be equal. We don't know. So this is no good. And this gives you the flavor of the difficulty with the comparison test. You have to establish an inequality going the right way with a good series. How could we answer this here? Observe that square root of n is bigger than or equal to 1. So if you add square root of n to both sides, and now cross multiply, and this series, which is 1/2 times the series 1 over root n, now you're good to go. Now this is a divergent p-series, where p is 1/2 less than or equal to 1. And so, since the smaller one diverges, the larger one diverges. By the comparison test. So that's the difficulty with the comparison test. Establishing this inequality, it has to be pointy, it has to be going in the right direction. Absolutely. Absolutely. This is for n equals 1, 2, 3, and so on. Right. So that's the issue with the comparison test. There is an easier approach known as the limit comparison test. Where establishing an inequality is not important. Limit comparison test says let AN and BN be series with positive terms. Right, again, all the tests we've seen so far are for series with positive terms only. So let AN and BN be series with positive terms, and suppose the limit as n goes to infinity of AN over BN exists and is L. If L is some number between 0 and infinity, then both series converge, or both series diverge. As somebody suggests, eventually positive is really all that matters. Absolutely. Absolutely. So even if the first few were 0 or negative, started wherever everything starts to be positive and you're good to go. Let's prove that. Let's understand why that's true. Again, the proof is nice and easy and just serves to explain why that is. If the limit exists and is some value of L between 0 and infinity, what does that mean? That means that, so proof, that means that for large n, AN over BN is very close to L. So AN is pretty much like L times BN. the two series behave in the same way. So if one series converges, then the other series converges, and vice versa. Both series, yes, thank you. Both series converge, or both series diverge. Absolutely. And there's the argument. These will behave in the same way. So there. Let's take an example. In fact, let's go back to the two examples we started out with. Right? We already convinced ourselves that this converges using the comparison test. Let's do it now using the limit comparison test. We don't have to establish an inequality. All we have to understand is the behavior of this function, the behavior of this term. And for large values of n, this -1 is insignificant. The numerator behaves like n. For large values of n, this +1 in the denominator is insignificant. The denominator behaves like n cubed. So this is going to behave like n over n cubed, or we're going to do a limit comparison with the series n over n cubed, or 1 over n squared, which is a convergent p series, where p is 2 bigger than 1. Let's do a limit comparison. We're going to take one of the terms and divide by the other. Doesn't matter which one is on top, which one is on the bottom. When you divide by a fraction, you multiply by the reciprocal. So this is n cubed minus n squared over n cubed plus 1. You can factor out an n cubed from top and bottom. Right? This has the form infinity over infinity, or you could do L'Hopital's rule. It's up to you. Let's factor out. The n cubes cancel out nicely. As n goes to infinity, 1 over n goes to 0, 1 over n cubed goes to 0, leaving you with a limit of 1. 1 is between 0 and infinity, strictly bigger than 0, strictly less than infinity. So both series converge, or both series diverge. This one converges, so this one converges by limit comparison. Questions? Let's take a few from the book. question comes up, do we choose the other function randomly? No. No. No, because if you choose randomly, you're going to have a lot of trouble. If you choose them randomly, I claim in a lot of cases you're going to get a limit which is 0 or a limit which is infinity. And you want to stay away from that. You want the limit to be finite and bigger than 0. So you need to choose the function or the other series wisely. You need to choose the other function which mimics the behavior of the function you had. Is there a pattern to choose? Well, you ask yourself, how does my series behave? What does it look like? And here you had a rational function. For large values, this -1 is insignificant. For large values of n, this +1 is insignificant. So this kind of looks like a n over n cubed or 1 over n squared, and that's exactly what we did. We chose 1 over n squared for that precise reason. Question becomes, can we choose 1 over n squared here as well? Notice that for large values of n, this -1 is insignificant. So square root of n squared is n, so the denominator behaves like 1 over n squared. And that's exactly what we're going to do. We're going to do a limit comparison with the series 1 over n squared, which we already know to be a convergent p-series. And let's see what happens. 1 divided by the other. Again, it doesn't matter which one goes on top, which one goes on the bottom. And if you flip it, n square root over n squared, you can cancel one of them out immediately. Factor out an n squared from the square root. And that becomes n square root of 1 minus 1 over n squared over n. I now cancel the remaining n's. As n goes to infinity, 1 over n squared goes to 0. So the whole limit is 1. Once again, 1 is between 0 and infinity. So both series converge or both series diverge. This one converges, so that one converges by limit comparison. All right. Consider this. Very nice question. What are you going to do? We'll do a comparison test. Real question is, what are we going to compare it to? And as a hint, let me remind you of this limit that you remember. I mean, maybe you don't remember. What is that limit? That limit is, anyone? And a quick L'Hopital's rule gives it to you. Limit is 1, thank you. Right? That limit is 1. So what does that mean? If theta is close to 0, sine of theta behaves like theta. So in particular, sine 1 over n is going to behave like 1 over n. And if you square it, so what are we going to do? We're going to do a limit comparison with the series 1 over n squared again. And it's unfortunate that it's always 1 over n squared. Again, complete coincidence. But there it is. Do a limit comparison with the series 1 over n squared, which again you know to be a convergent p series, blah, blah, blah. So sine squared 1 over n over 1 over n squared. All right. Which is really, I mean, we can cheat here and say that this is sine 1 over n over 1 over n, the whole thing squared. And if I just evaluate this limit, which has the form 0 over 0, so I can do a quick L'Hopital's rule. Derivative of sine is cos times minus 1 over n squared. Derivative of the bottom is minus 1 over n squared. And these cancel out nicely. As n goes to infinity, 1 over n goes to 0. Cosine of 0 is 1. So this is going to converge to 1 squared, which is still 1. And again, 1 is between 0 and infinity. So both converge or both diverge. This one converges, so that one converges by the limit comparison test. How are we doing? We have time for one more? While the limit comparison is very nice and simple to use, it doesn't answer every single question. No test answers every single question. And here I don't see how the limit comparison test could be used. I think we're going to have to do a straight up comparison test. And let's observe that, first of all, all the terms are positive, so a comparison test is fine. And what is this? We saw in factorial last time, what was that? This is the product, 1 times 2 times 3, all the way to n. And to the n, you've got n copies of n. So n times n times n, n times. So if you break this up into a bunch of fractions, let's leave the first 2 fractions as is. And then you've got a 3 over n, 4 over n, 5 over n, all the way to n over n. They're all less than 1. So let's replace all of those fractions by 1. In other words, what are we saying? N factorial over n to the n is less than or equal to 2 over n squared. And 2 over n squared, which is 2 times 1 over n squared, is a convergent p-series. So if the large series converges, the smaller series converges as well. Well, so this converges by comparison. Why do you stop at 2 over n? Because it works. You don't have to go any further. Well, I mean, what are the other terms? You had a 3 over n. So think of n as a very large number. Take n to be 20. That's not very large. But 3 over 20, 4 over 20, 5 over 20. All these fractions are less than 1. 19 over 20, and then 20 over 20, which is still 1 anyways. So you can replace all of them by 1. How are we doing? Everybody comfortable with that? Now this is essentially where could you rewrite the series as 1 over n to the n minus 1? I don't know that you could do that. No. And convince yourself, what are we saying? 1 over n to the n minus 1. Convince yourself that these are not the same. Just take any value of n other than 1. If n is 2, you're already in trouble, I think. Or maybe 3. Correct. 1 over n and 2 over n are also less than 1. But if you make this less than or equal to 1, this is not a convergent series. Whereas 2 over n squared is a convergent series. So this won't help you. And if you stop at 1 over n, still doesn't help you, because the series 1 over n is not a convergent series. Exactly that. So that's where we left off in 141. So for those of you who took 141 last semester, from now on it's new material. Exactly. The only reason we take the first 2 terms is to get a convergent p-series. Absolutely. So I will post a web work probably tomorrow after class. How are we doing here? Questions, anyone? So tomorrow we'll look at other tests, new tests that we haven't seen in 141, in particular ratio and root test. And then we'll ask the question, what about series that have both positive and negative terms? All the tests we've seen so far have to do with series with positive terms only. So we're going to investigate that as well. You could add a 3 over n here and get a 6 over n cubed, and the conclusion would be the same. The conclusion would be the same, that the series converges, because this would be a convergent P series as well. So it does not matter, correct? Questions? Anybody? No, we're good? Vinit had a question, I think. You want to give me the series you were talking about? Any questions from anybody else while we're waiting? No? Vinit, are you still there? Maybe not. I'll give you another minute in case you are and you're just typing away. Anybody else with anything? No? We're good? Yeah, I understand he's probably not in our class. Still, though, if he had a good question about series, I'll certainly take a moment. Yeah, go ahead. Go ahead with your questions. And Ran as well. Please go ahead. All right, folks, I'll give you another minute, but I don't see any questions coming up. 2 people have asked to post questions, but then no questions. Still typing, very good. Fine. So I won't, wait, not that? Well, so Vinit is asking for this, I assume. Start with the series for 1 over 1 minus x. Fine. Well, so let me do Vinit's first. No, not that one. All right, so back to Rand. You're saying ln of that minus ln of 1 minus x. Very good. And Vinit just wants the ln of, oh, but ln of that is the same as ln of 1 plus x over 1 minus x. So perhaps that and I see now that that was your original question as well, right? So it's the same thing. So either way, let's do this one. The usual. Take the derivative. So I mean, first you're gonna do find two of them, right? Find the series for this, which you do by taking the derivative. And the derivative is 1 over 1 plus x. So you can find the series expansion for that the usual way, the trick. You know what trick. This is 1 over 1 minus negative x. And then go back by integrating. Integrate term by term. Do the same for this one. The derivative of that is negative 1 over 1 minus x. Find your series expansion for that and integrate to go back to that. And then subtract the two. That's it. We'll get there probably by the end of the week. On Thursday. Yeah, so I mean, you should be good. That's the way to do it. Very good. Thank you, ladies and gentlemen. I will see you tomorrow. Same time, same place. You guys have a good one. Oh, Vinit, very well. I thought, go ahead, what is it? Well, I mean, you're saying e to the above expression? Is that the one you're? Yes. Are you saying e to the ln 1 plus x over 1 minus x? Is that the one you're talking about? Is there a lag? I mean, look, I can't Please just write what you want me to discuss. I don't see what you're referring to. I mean, you're referring to something I don't even see on the screen. I have probably thousands of posts. Why don't you copy and cut and paste? Copy and paste the expression. Sum 1 to infinity, so a double sum, very well. What's the expression? Yeah, I don't know. Or BX. Maybe. I don't have a good answer for that right off the top of my head. I'd have to think about that. Yeah. All right, sorry about that. I mean, my suggestion, if I could, is maybe work out the Bernoulli number. Yeah, I know. Sorry, nothing. I'll think about it. Let me think about it. Maybe. All right. Thanks a lot for coming, guys. I'll see you tomorrow.